See ya. What's up? But like,
I will begin with a word of prayer. Let me get started here. Heavenly Father, we thank you for this opportunity we have to meet together and study your creation. I pray you would help us use this time wisely to just review for the upcoming test too, Lord. In your name I pray, Lord Jesus. Amen. So if you guys have questions about the grading of Mission 1, that's, I would say that's interesting, but that's a lie. But you can ask me after class. Don't ask me now, obviously. Let's see here. Are there any questions about the material? So what should I put on test 2? What do you guys think?
Inclined planes.
Inclined planes, maybe physics that we've studied after test 1, right? Probably.
Work along a straight line.
So, you know, a similar question might be, what's the deal with problem 32, was it? I don't know what that was about. So well, let's see here. You can do it. All right, so let's see here. So is there any particular one you guys like to talk about? Not really. I was going to say this problem, where was that thing? Not 32, 37. Like, what's the deal with this problem? I don't know. I mean, this is a test 1 problem, right? So you should think I'm helping you review for the final. That's what this was, okay? So I'm sorry I've asked you an old question. I must have meant to like do something annoying to make it different, and I just forgot to. So yay, easy problem, comparatively speaking. Any questions? Yep.
Can you do number 39?
I can talk about it. I haven't had a chance to check my answer, so I'm curious if you guys got the same thing I did. Because what I got was nuts.
like 360,000 meters.
More. So first of all, to find the work done by the explosive gases, I integrated the alpha x minus beta x cubed along x, because that's what I'm, to find the work done, I just integrate. It's one-dimensional motion when it's in the barrel, and x is along the direction of the barrel. So, that would give me the work done, which in terms of the calculus here works out to, if I did it right, 100 times alpha divided by 2, and oh man, that was supposed to be a 4 there. I wrote 3 because I'm an idiot, and I whited it out, and I was going to come back and write a 4 there, and obviously well, there's a 4 there, but it's in white. Okay, don't try that when you argue points with me. It won't work. So anyway, I got this formula for the total work done. Of course, that's equal to the change in kinetic energy. It starts with velocity 0, and the ending velocity is the starting velocity for the projectile motion, so I just called it v naught, And I solve for v naught squared, because I know that's what I'm going to need for the range formula. 45 degrees gives me the maximum range, because we're starting and ending in the same level. So, yay, no calculus there, just v naught squared over g, I believe. Yeah, so when I plugged the numbers in, it was big. It was really big. The mass was 3 grams, yeah? So that ends up giving me a 0.3 squared down in the denominator, because that comes from, oh, wait a minute.
That'd be 30 grams.
Oh, rats. I didn't need to square that. I'm a dummy. Oh, this is wrong. Let me fix it. Whew. Like I said, I haven't checked my answer yet. I'd love to tell you that that's the least stupid thing I did today. It's not true. Not even close. No. You got to know when you're beat. Let's see here, 5,000 times 20. What? Wait a minute. Okay, good, that's positive. I was worried that this number inside the parenthesis was negative, but it's positive, yay. And I divide that by 0.03. I just divide by 0.03. And then, oh, that's 666666666. Okay, divided by 9.8. 680.3 kilometers. That's what I got. So correction, what I got when I actually did not make a stupid algebra mistake was 6.803 times 10 to the 10 to the 5th meters, aka 680.3 kilometers. Which I'm pretty sure means that this is an inappropriate use of the kinematic equations. How far is 680 kilometers? Is that far enough for the curvature of the Earth to matter? Yeah, then it's probably far enough for us to not be using force of gravity is just equal to mg, right? Probably, to be accurate here, I should look into the inverse square law way of thinking about things. So, which would be something we haven't done in here. What I'm saying is, even with my adjustment, like this is just crazy. This number is like beyond Earth scales, right?
We found the solar system.
Well, how big is the Earth? Like 6,000 what? 6.3 million, 6,000 kilometers, isn't it, radius?
At least.
So, at least. You're like, the Earth is flat, so. I mean, if you want to say that, that's fine, but then you need to tell me where the four corners are. So, that's all I'm saying. Anyway, does that, let me, setting aside my stupidity in terms of punching numbers in. Actually, I wish I could claim it was punching numbers, but I decided to square. I already solved for v naught squared. I should have just plugged in that formula for v naught squared, right? I will fix this and repost it, obviously. But the larger point here, the idea is this. To calculate the work done by a force in one dimension, we just integrate the force, right? That gives us the work done. But that work is related to the change in kinetic energy. So that gives me the initial energy, the initial kinetic energy of the bullet, which tells me its initial speed, which then I can use the usual kinematic equations to find the range. And since its beginning and ending height are the same, the formulas are already like known, right? We have formulas that we can just use. I mean, sometimes we have to do calculus. This is not one of those places. Past the initial finding the work done by on the bullet by the explosion of the gases part. Yeah. Does that make sense? Modulo my stupid arithmetic mistake. Other questions? Yeah.
Real quick, what was the mistake? Was it the m squared?
Yeah, it's that. Well, it's the I solved for v naught squared is this, right? So I should just plug. I shouldn't square it. I should just plug in 100 alpha minus 5,000 beta divided by m. So this shouldn't be squared, and the m shouldn't be squared. So, yeah. Yep.
Could you do the problem with partial derivative?
A problem with partial derivatives. Let's make a new one. So, example, let's let our force be equal to, I don't know, let's do minus yz plus cosine x and minus xz plus e to the minus 3y rather. And for good measure, let us throw in a minus xy minus 4z cubed. There we go. There's a fun force. given particle moves from, let's say, the origin to the point 1, 2, 3, starting from rest, and having final velocity, let's say final speed of, let's say 100 meters per second. If the mass of the particle is, say 50, well, let's say 200 kilograms, then find F1 such that F net is equal to F1 plus, let me call this F naught. F naught. So let me explain the situation here. We got some motion. We're starting at the origin, at rest, and we're moving up to the point 1, 2, 3, right? Along some physical trajectory. I guess I shouldn't say find F1. I should say find, I don't want to say find F1. I want to say find W1 such that F net equals F1 plus F naught, and W1 is equal to the integral along the path it travels of F1 dot dr. In other words, I'm asking you to find the work done by the forces other than F naught. So the net force is the sum of two forces. It's the sum of the given force F naught and a mystery force F1. I'm asking, what's the work done by the rest of the forces acting on the mass? We're not given those forces, right? We don't know them. What we do know is that it's got initial velocity 0, and we know it's got final velocity 100 meters per second. So how does that help? Well, let's think about this. So the network, right, is equal to the work done by 1 plus the work done by the 0 force, right? But it's also equal to the change in the kinetic energy, right? But we can calculate the change in kinetic energy because we know it starts at rest and we know it goes to 100 meters per second, and we know the mass, right? So we're trying to find work 1. So work 1 then is going to be equal to the change in kinetic energy minus the work done by F0, which is what? Why would the work done by F0 be 0? What is W sub 0? Like, more specifically, W sub 0 is equal to the integral along the curve of F0 dot dr, right? The work done by that. At the start of all this, you guys asked me for a potential energy example, right? So let's get to that. In fact, F0 is conservative, right? Let's work it out. What's the potential? So my point to you is that this is actually going to be equal to, like, minus the change in U, let's say U naught, because it's the potential energy just for the F naught force. So that would specifically be like U of the origin minus U of 1, 2, 3. What is U? All right, so the, well, let me put that thing up so I have room to work here. So let's work it out. What we need is for F naught to equal minus the gradient of the potential energy U sub naught, what we need is partial U naught partial x equals to what? Partial U naught partial y equal to what? Partial u naught partial z equals to what? So what do we have to have there? We have to have what? Yz minus cosine x. We have to have xz minus e to the minus 3y. And we have to have xy plus 4z cubed, yeah? So let's integrate each one of these equations holding the other two variables fixed. So let me suggest doing an integral, with respect to x. Integrate in y. Integrate in z, all right? So integrating with respect to x, I get u naught is equal to xyz plus sine x, right? Do I get that actually? Is it minus sine x? All right, cool. So minus sine x plus c1, which is in principle a function of y and z. On the other hand, we get u naught is xyz. Let's see here. Plus, I think, 1/3 e to the minus 3y. If I differentiate this with respect to y, I get back my xz, and I get, by the chain rule, minus 3 over 3, which is minus 1, yay. So that's good. And then, technically speaking, plus c2, which is possibly a function of x and z. Integrate in z. I get u naught is equal to xyz. Let's see here, plus z to the power 4. And then plus c3, which is in principle a function of x and y. So the way this works is you got to imagine that this, like for instance, this c3 of x is actually including what? It's including like, what's it including apparently? It's including like this term and also including that term. Like both of these are in there, is the way to think about this, all right? Anyway, so my instructions for you, a strategy to find the potential energy function is integrate each one of the components respectively with respect to, x, y, and z. And then you take those three things and you merge them. And then you check your answer. So u looks like to me is going to be x, y, z minus the sine of x plus 1/3 e to the minus 3y plus z to the power 4. And you could add a constant to all this if you wanted to, but hey, that'll work. So there you go. That's the potential energy function for just the F naught force. In this particular motion, that's not the potential energy for the net force because the net force might not be conservative. I don't know. Probably not. I don't have enough information to decide whether or not it's the case that the net force is conservative, okay? For this problem that I just made up. So now that we have that, yeah.
How did you know that F is conservative?
Because I made it up. Because we just found the potential energy. So how do I know it's conservative? Well, you can check it out, right? Like calculate minus the gradient of u naught and you will get F naught. So if that's the case, it's conservative by definition. But how did I know it was going to be conservative? I made it up so that would happen. Yeah, yeah.
And then with going from the XYZ, for that to be in front of original potential energy, why wouldn't it be like times 3? Or why is it just XYZ?
Does the gradient of what's in the box give you the force?
Yes.
Then it's the right potential energy. It's, I mean, If you want, I can derive it through a more laborious, lengthy way, but
I just was wondering why the XYZ.
if I put a 3 here, when I differentiate it with respect to x, I'll get 3yz, for instance. But I don't need 3yz. I need, a minus yz. If I put a 3 there, it spoils it. This single term of xyz automatically gives me this term, and that term all at once. It's a 3-fer.
Okay.
Yeah.
How would you find the potential energy for a non-conservative?
How would you find the potential energy for a non-conservative force? I like this question. The answer is you wouldn't. So it's impossible. Like, by definition, potential energy only exists for a conservative force. So a conservative force F, 3 ways to look at it. Number 1, F is equal to minus the gradient of the potential energy function. Number 2, F is path independent. And number 3, the integral around a loop is equal to 0. These are our 3 equivalent formulations of a conservative force. A conservative force either integrates around all loops to give 0, it gives you the same work with respect to coterminal paths. If I have 2 paths which begin and end at the same point, the work done by the force is the same over both paths. If that's true for all possible paths, the force is said to be path independent. And finally, if the force is equal to minus the gradient of a potential energy function, it's conservative. Any one of these 3 conditions gives you the other 2, all right? And as such, we can derive from the fundamental theorem of calculus for line integrals that the work done by such a force over such a curve is minus the integral of the gradient. And as we worked out, that's minus the change in u over the curve. But on the other hand, if this is also the net force, then this is also equal to the change in kinetic energy. And that gives us conservation of energy, assuming that it is the net force. Because if the change in kinetic energy is equal to minus the change in the potential energy, that means that, potential energy plus kinetic energy is held constant. All right. Anyway, let me finish this problem. So what is u of 0, 0, 0? What happens when you plug in the origin into this formula? You get what? 0, 0, 1/3. So that's 1/3. What's u of 1, 2, 3? A headache. What's 1 times 2 times 3? Hey, can I change this 1, 2, 3 to something else? Or anybody actually worked this out already? Nobody? This would be much nicer if I just put a 0 here. If I put that 0 there, then the xyz is 0. Yay! And the sine of x is, I should have put the 0 on the side. Oh, anyway, fine. I'll take my medicine. Minus the sine of 1 plus 1/3. It should be minus 1/3. Because e to the e to the 0 is 1. And then plus 1. Yes, it would be plus sine of 1. Thank you. Thank you, Gabe. Minus a minus gives me a plus. Very good. And then, 3 to the 4th power, 81. All right, so you got yourself, basically it's equal to 81. But I'll work it out. So, is that minus 81? Ah, man. Thank you. Yeah, you're right. Thank you, thank you. I asked if anybody done it. Nobody spoke up, so I changed it. This is why we can't have nice things. You guys got to, if I ask a question, you got to answer it. It's your sign of. It is. It's always your fault. Let's see here. Of course, this is my class. It's the student's fault. I get to decide fault. I choose student. Let's see here. No. What do you think? Are we working in degrees or radians? We did calculus, right? That is radians. If I differentiate cosine and it gives me minus sine, we're working in radians. Excuse me. A sine of 1. Man, stupid voice. Oh, these cancel, right? Sine of 1 minus 81. So I got minus 80.16 for the work done by F naught. But minus a minus gives me a plus, right? So changing kinetic energy plus 80.16 apparently. And we're going to assume that that has units of joules. I will soon not be talking at this rate. Where are we? So my mass was 200 kilos. So I have 1/2 times 200 kilograms times 100 meters per second. I square that thing. Because the change in kinetic energy is what? The 1/2 mvf squared minus 1/2 mv naught squared. But v naught was 0. So the initial kinetic energy was 0. Final kinetic energy is this. And so what do we got? Goodness gracious. 100 squared. Whoa. Whoa. Dude. Yeah, 1 million. Well, that's annoying. 1 million. 4 zeros here. 0.16 joules. So in other words, 1.000008016 megajoules there. There we go. So that's the work done by F1. I should have made the mass smaller. It would have been more interesting, less zeros. The larger point that I'm trying to communicate to you guys is even when the net force is not conservative, we can still use conservation of energy with respect to a force which is conservative. So sometimes you have situations where you've got a mixture of conservative and non-conservative forces, right? We still have the potential energy function for a conservative force to work with, even when it's in the presence of other things like friction or some unknown mysterious rest of the force that's making up the net force, like in this problem. So. Other questions?
I apologize. Could you repeat what you said about using that for forces that a mixture of conservative and non-conservative forces?
Well, the point for this example, there is no energy is not conserved overall. In the sense that I don't know what the net force even is. All I know is a snapshot. I know that initially it's got 0 kinetic energy. I know that at the end of this trajectory it's got 100 meters per second. So work was done, right? And work was either done by the force which I'm given, or the forces I don't know. All right. So I'm just using F1 as a label for all of the forces acting on the mass that are not the given force. Apparently, those have to do 1 million, a little bit more than 1 million joules of work on this system to achieve that motion. I don't know what they are exactly, right? Now I could make it so that you could figure out the precise force if I gave you a lot more information. If I said, like, suppose the rest of the force is actually a constant force. What constant force would be required to achieve this? You know, if I give you that information, you could find a specific constant force which would achieve this. That's possible. If I did that, then the net force would actually be conservative, because a constant force is a conservative force, and the sum of two conservative forces is a conservative force. Why is that? If I have conservative force 1 and conservative force 2, what's the potential energy for F1 plus F2?
Potential energy of 1 plus potential energy.
Example 3. Let us suppose we have this situation. What's the potential energy for the mass what's potential energy would be equal to, right? So we could, we could suppose like this is the equilibrium. And equilibrium here would be when the spring is stretched what? Like if you just laid the spring flat
Without tension?
without any tension, and then you let it go vertical, how much would it stretch from its like natural unstretched length? It would stretch by the force of like, it would be like mg equals to, k y naught, right? So like it would stretch by mg divided by k. That's how much it would stretch. I'm like just making y equals to 0 when it's already stretched vertically. Anyway, so with that said, excuse me, the potential energy here would be what? Tell you what, let me call that y naught. Let me just work it out here for a second. So this would be y equals y naught. So I would want 1/2 k, let me write it out this way, the distance that the spring is stretched, and then plus mg, let me just call it z for the sake of just thinking about things here for a second. So well, let's just say I want the distance from the equilibrium. So let's say like y minus y naught. That will give me the potential energy due to gravity there. What's the distance that what's the distance squared here? So I have what, 1/2 k times y minus y naught squared plus mg y minus y naught. That'd be the potential energy for this system. If I was to, yeah?
Excuse me, so would y always equal 0 in that equation then? Is they're equal to each other?
Well, that's just the equilibrium condition. If we stretch it past that, then it's going to oscillate up and down. If that's where it started, that's where it would stay. If y is equal to y naught, the motion is very boring. It just sits there. But if I pull it a little bit, then I stretch out the spring, and then it's going to pull it back up. And then gravity's going to pull it back down, and then so forth and so on forever and ever, if there's no resistive force. Yeah?
So basically y naught's that constant there, and then if you pull it, y is positive or negative depending on that.
Right, yeah. If y is greater than y naught, then we're compressing the spring upward. If y is less than y naught, then we're stretching the spring downward. But here's the thing. So this is a one-dimensional problem, right? In a one-dimensional problem, this is the potential energy as a function of y. What's the force? The force, in this case, is minus du dy. How's that work out? And does that make sense? So when we differentiate this, we get what? We get, minus k times y minus y naught minus mg. And what are we looking at here? This is the spring force, and this is gravity. What prompted this example was I asked you guys what's the net potential energy if there's two conservative forces involved. The answer is you just add the potential energies. Right? The potential energy of spring force plus gravity force is exactly the potential, the potential energy of the spring plus the potential energy due to gravity. And when we differentiate, the derivative of a sum is the sum of the derivatives, so it all works out. Other questions? Yeah. 25. You guys can also ask me about mastering physics if there's something in there that you want to talk about. Oh, 25. So if 25 was ever so different, like just modified ever so slightly, there are both methods of investigation are possible. If I made it a square instead of a cube, you could potentially hack the integration that's at the bottom of this for the square. But for the cube, I think it's a bit much. So the method here is somewhat conceptual. The terminal velocity is when when the velocity is maximized, right? How would the velocity be maximized? That means that dv dt is 0, right? By the critical point theorem of like calculus 1. To maximize something, we make the velocity 0, but make the change in the thing 0, but the change in the velocity is acceleration. When acceleration is 0, well, that's meaning that the sum of the forces is 0, right? So in other words, that's when gravity and the friction force balance out. So we have the situation that, 0 has to be equal to minus mg minus beta v cubed, which I can solve and get that the, probably I'm supposed to have a minus in here, my bad. I think I'm missing a minus. Yeah, so sorry about that. So probably should be a minus here, but yeah.
So what if we kind of drew a free...
Well, that's the speed. So the minus pulls out of a cube root. It's not imaginary. It's just minus pulls out a cube root. So that's the speed. It's not the velocity. The velocity would be negative because it's falling. So the minus is not a math mistake. It's just, I should have a minus in the answer really, because the terminal velocity is negative with this setup. Yeah. Yep.
If we set up a free body diagram and had the velocity or positive going down towards the Earth since it's falling,
Yeah.
and we got positive, would that be acceptable? Because then
No, if you had downward as positive, then the equation should be ma is equal to mg plus beta v cubed.
it still wouldn't be minus beta v cubed.
Will be minus beta v cubed. Oh, okay.
You're going down, but friction forces pushing back up.
I think this is right though. If v is negative, this is positive. So v is negative, minus a negative cubed is a negative, negative is a plus. So for beta being a positive constant, I think that's the right sign convention. So if I put plus mg, I feel like I should also have to put plus beta v cubed to be consistent. So I'm going to have to disagree. Yeah.
Even if you have velocity or positive going down, so the velocity would be positive.
I'm just saying in whatever system of whatever convention you make, the signs should be shared by these. Like if I'd have to think. I don't think you're right, but I'd have to think more about it. Yeah. Other questions? So did that explain 25 to you? Like basically set force being 0. The terminal velocity happens when the frictional air force balances with gravity. That's terminal velocity. So thankfully we don't need to do the integrate, like to actually work that out here. Goodness gracious, look at this mess. The integral of this 1 over something cubed is actually this. And then after all that, you just got to solve for v and let t go to infinity, right? Ha. As I said, ha. I can hack this calculus for like the square friction. Then the integral is just like a hyperbolic substitution. It's not too bad. But for the cube, oof, it's nasty. Let's see here. There we go.
Can we go over in the mastery
Yeah, which one?
6.76?
I'm scrolling too fast. 6.76.
I'm still
It's this one again.
But I've talked about this a lot. So what's the question exactly?
I'm still struggling on C and D because I don't know, for some reason I get a maximum, or I get the position of the maximum speed to be 0.015 meters.
Yeah, I don't know what to tell you right offhand. Like, I can't solve that in 3 minutes. I can tell you guys how this problem basically goes, though. The idea of this problem is that there is, you've got a spring that is compressed. You have potential energy rather in the spring, and then that potential energy is released as the spring is released, and it pushes the mass through the barrel, right? So something like this, and then at the end of it, you've got like that. So it's stretched out. So this, your potential energy is 1/2 k times the compression distance squared. But this is, over here you've got a constant force, resistive force against it, right? So the way to think about this is, as the spring pushes the projectile through the barrel, the friction force is going opposite, right? It's taking away your energy. And so you should have the initial potential energy minus the force, the resistive force, times the distance that it goes, which is given to you, I think, to be 6 centimeters, or, well, mine is 6 centimeters, or whatever. And so that tells you how much energy is lost. And when it gets to right here, there is no potential energy because the spring was compressed as much distant, like the compression of the spring matches the distance that it unstretches. So the potential energy, as I read the problem, is 0 right when the bullet leaves the end of the barrel, which means that it should have the kinetic energy, which is given by the initial potential energy minus the work done by the resistive force. And you should be able to solve the problem with that principle, which is what I told you before, but you said it didn't work out. So I don't know. But let's see here, for mine, these are the numbers that come from mine. So the and the maximum speed, where does that happen? Where would maximum speed happen? That's where the velocity is maximized. Where's the velocity maximized? Where dv dt is 0. Where is dv dt 0? dv dt is acceleration. Where's the acceleration? 0. Where the net force is 0. What's the net force? Spring force and the resistive force, right? So you're looking for where kx is equal to the resistive force. That should give you the x where the maximum speed occurs for this problem. And it happens to be, for mine it's 5.2, whereas the speed it leaves the barrel is 4.9. But anyway, I wish you well. Have a good weekend. Sorry I didn't have any highfalutin visitors. I'm not a government professor. What can I do?